Swayam Prabha. Digital India. Educated India.
So let's go back to the simple case where there is no offset, and let's ask, how do we invert the Lorentz transformations? That is, supposing I know the coordinates ct prime, x prime, y prime, z prime of events as described by an observer S prime, how would observer S prime translate his coordinates into the coordinates of the observer or the frame S? Okay, how would observer S prime get from his coordinates of space-time events the coordinates of the frame S? Okay, so what we need to do is we need to invert Lorentz transformations. And so, since we obviously have this relationship, which is just a linear matrix relationship, okay, we're assuming no offset for the moment, then all we have to do is invert this matrix, lambda. Okay, so Ct, x, y, z would just be the inverse matrix of lambda, which depends on eta, times ct prime, x prime, y prime, z prime. This would be the inverse Lorentz transformation. So let's work out the inverse of this matrix, cos eta, sinh eta, or minus sinh eta, cos eta. Okay, and it's not hard to work out the inverse. I won't do it here, but lambda inverse you can show would just be cos eta plus sinh eta plus sinh eta cos eta, and then the rest of the matrix is the same. So what this tells you is that if I want to go back from observer S prime to observer S, or the frame S, what I would need to do is I just need to use the same transformation matrix with parameter minus eta. Okay, so in other words, if I want to go from observer S to S prime, I use a transformation parameter eta. If I want to go from S prime back to S, I use a transformation parameter minus eta. And since eta is, or tan hyperbolic eta is beta, and beta is V by C, and you'll recall that tan hyperbolic eta is an odd function, which means as eta goes to minus eta, beta goes to minus beta, and V by C goes to minus V by C. Okay, so that means if I used a parameter V, to relate S and S, or go from S to S prime, I would use a parameter minus V to go from S prime to S. That is fairly satisfying, especially from the point of view of Galilean relativity. If the frame S prime is moving at a speed V relative to the frame S, then the frame S is moving relative to S prime at a velocity or a speed, or a velocity rather, minus V. Okay, that is, it's moving along the negative x direction with a speed V. Okay, so transformations and inverse transformations are just related by a change of V to minus V, or eta to minus eta, or equivalently beta to minus beta. Now, another interesting thing to do is if we go back to our plot of gamma versus beta, most of everyday objects have speeds which are much smaller than the speed of light. Okay, the speed of light is incredibly large. It's 3 times 10 to the 8 meters per second. But if you take, for example, let's say someone walking down the road, maybe you're covering a typical distance of a meter every second or so. So it's many orders of magnitude smaller than the speed of light. Okay, even if you take a jet plane and see how fast that travels, or even the speed of sound in air, right? Those speeds are very small. The speed of sound in air is 330 meters per second, or if you approximate that as about 300 meters per second, that's still 1,000,000 times smaller than the speed of light. Okay, so for almost all everyday objects, the speeds that we're looking at live down here. Everyday objects have speeds which are over here. And we'd like to understand what happens to this dictionary in the limit of those small speeds. Okay, what we would expect is that you should just get back the dictionary of Galilean relativity at small speeds, because that's something that that is intuitive to us, and we see works to a very good approximation for our everyday life. Okay, for everyday speeds. So another interesting thing to do will be to ask, what happens to Lorentz transformations, or this dictionary of special relativity, in the limit v much less than c, or equivalently in the limit where of everyday speeds, okay, speeds that we're familiar with on a daily basis. So first, let's look at the equation for x prime. So x prime, which is the coordinates of the moving observer relative to a frame S, would look like this. It's 1 over square root of 1 minus v squared by c squared into x minus vt. Okay, so in the limit that v is much less than c, x prime is approximately x minus vt. So this is very good because it tells us that we recover one of the transformations of Galilean relativity, which is that the position as measured by the moving observer would just be related to the position as seen by the original observer minus vt. Okay, but now we also know that time is relative. Okay, that is the time t prime as measured by the second observer is not going to be the same as the time t as measured by the first observer. What happens to the relativity of time in the limit that the speeds are much smaller than the speed of light? So for this, let's look at the relationship of t prime to t. So t prime is 1 over the square root of 1 minus v squared by c squared into into t minus vx over c squared and x prime is, we'll just write this out, is 1 over 1 minus v squared by c squared times x minus vt. Now, when we talk about time, we have to be a little careful. We should talk about a specific clock, that is a clock moving with a specific observer in the frame S prime. So let's take the observer in the frame S prime who is moving with a speed, who is located at the position x prime is equal to 0. Okay, let's take a specific observer in frame S prime. And we will ask what is T prime for this observer. Okay. So for this observer, what we would have to do is we'd have to invert these relationships. So first let's invert those relationships. So we can write, and we already saw that the inversion just means that we replace v by minus v. So we would just write t and x as t plus, or t prime plus v x prime over c squared. And now, since we're fixing the observer x, to be at x prime is equal to 0, okay, that gives us t is 1 over square root of 1 minus v squared by c squared t prime. This is an exact relationship. However, if we go to the limit that v is much, much less than c, then that gives us t is equal to t prime in the limit v much, much less than c. So time ticks at the same rate for both observers in the limit of everyday objects where speeds are much less than the speed of light. And the relativity dictionary just boils down to the Galilean relativity dictionary. Okay, in the limit that the speed is much, much less than the speed of light. So let's summarize some of the key features that we've learned of Lorentz transformations. Lorentz transformations. One is relative speed v. Okay, I'm allowing it to be positive or negative, but the magnitude of it should be less than c. Okay, if you want a valid dictionary, which means two inertial frames S and S prime, or the frame S prime as seen in the frame S, can only be moving at a speed smaller than the speed of light. That's the only case where this dictionary is valid. Second, if I want to go from frame S to frame S prime, I use a velocity transformation parameter v. Then the inverse transformation to go from S prime to S just uses minus v. Okay, so this is about the inverse transformation. And finally, we saw that in the limit that the speeds v by c is much, much less than 1, okay, or that is for small beta or equivalently small eta, we saw that we get back Galilean transformations, which is why the ideas of special relativity did not really come about until we began to study light or things moving close to the speed of light. Now let's discuss some observational implications of the special relativity dictionary. Okay, and clearly these observational implications will become important as the speed of these frames relative to each other becomes comparable to the speed of light. So the first implication comes from the equation or the dictionary from the transformation of time. So we saw that Ct prime is 1 over square root 1 minus v square by c square Ct minus Vx by c. Or let me just erase this and let's go back to the original equation that we had written down in terms of t rather than Ct. Now, what does this tell us? Okay, so imagine that you're in a frame S. So it's like you're standing on that railway platform and you are one observer O over here, and you have a bunch of friends who are separated from you by fixed distances of 1 meter, say. So you have all these friends, and now a train goes past you, and that's in frame S prime. And at any instant of time in your frame, there's a well-defined instant of time where all of you have the same value of time on your clocks. But as we've seen before, this well-defined instant of time is not the same instant of time as seen by observers on the train. So if I look at observers on the train, and if we were to look into their clocks, the clock readings on each of their clocks would not show the same value. Okay, because the instant t is equal to 0 here and the instant t is equal to 0 here, which can be attributed to the events of, let's say, observer O and O prime meeting each other, and friend 3 and friend 3 prime meeting each other, the event O and O prime meeting each other is not simultaneous with the event friend 3 and friend 3 prime meeting each other as seen by observers on the train. They are simultaneous as seen by the ground observer, but not simultaneous as seen by the train observer. How do we see this from the Dictionary of Special Relativity? Well, the Dictionary of Special Relativity tells us that the location x is equal to 0, t is equal to 0, which is where O is located, is the same as the location where t prime is 0 and x prime is 0. Okay, that is where O prime is located. So t prime would be 0 here. But if we ask what happens to the time on the clock that friend 3 prime sees when he comes face to face with the friend f3 sitting on the platform, well, what we would see is from the Dictionary of Special Relativity, this t would be 0, okay, but x would be plus 3. So therefore this time would be negative. Okay, that is, this time would occur earlier according to the train observers compared to the event of O meeting O prime. So in other words, friend 3 prime would appear to meet friend 3 before O prime met O, or before they came face to face. And similarly, if I look at friends to the right, let's call these friends 4, 5, and 6. Friend 6 would appear to have a positive time on their clock when they come face to face with friend 6 on the ground. Okay. So that means that they would meet friends, according to the train observers, friend 6 prime meets friend 6 prime, friend 6 later than when O prime meets O. Okay, so if the observers on the ground look into the train and just read the times on the clocks of these friends, they would see clocks which appear to be out of sync with each other. Okay, so the clocks on the train appear to be out of synchronization as seen by a ground observer, or as seen by the ground observer. Okay, so clocks on the train, that is in the frame S prime, as seen by the ground observer in the frame S. All right, and not only do they appear to be out of sync, the synchronization grows worse as you move further to the right or you move further to the left. Okay, so these clocks look like they are showing more and more negative times. Okay, so synchronization appears to be worse further away from the origin. And the last point is, or the clocks on the train appear to be negative, that is to say that they are behind as we go along the direction of motion of the train, and they appear to be running, or they appear to be offset ahead. Sorry, running ahead is running behind is the wrong word, as we shall see. There should be offset behind versus offset ahead as we go opposite to the direction of motion of the train. Okay, so the clocks over here appear to be showing times earlier than t is equal to 0, and more and more early as you keep going to the right. And the clocks to the left appear to be showing times later than t prime is 0, and further, more and more later as you go further to the left. Now, what about the rate at which these clocks tick? Okay, so this only tells us at an instant of time, t is equal to 0, as seen by the ground observers, that the clocks on the train appear to be out of sync. But what is the rate at which the clocks on the train appear to tick? Well, that is a different question. So the first thing that we saw is moving clocks appear to be out of sync. But now we can ask a second question, which is, what is the rate at which the moving clocks tick as seen by the ground observer? Remember, according to the train observer, nothing unusual is going on, right? Their clocks are all in sync with each other, okay? And their clocks are ticking at exactly the same rate as they would expect. They don't see anything strange about the rate at which their clocks are ticking. It's only when you make a translation to the ground observer and the ground observer is trying to interpret what the train observer is seeing that you run into these strange things.